Good morning. On the 10th day of February, things are going fast. I have lots of cool things to talk about in my mind, both software tools today and modeling and analysis tools in the Fourier domain, including autocorrelation and power spectral density, which are two new things you haven't seen before up until now, and then some applications on how they work. I also want to give a report on how I think things are going. I graded, I think it was 3 papers I completely graded last week. Everything there seems to work okay. I mean, did everybody work them perfectly? By no means. You guys made careless errors, which is kind of a normal, unfortunate occurrence. So, it's not devastating, but it's just like you forgot to square something, so the numbers didn't come out right, because it was magnitude squared in the energy calculation, which more than one person made that same mistake. So it just shows you how easy it is to slip up on stuff. I did not get the old quizzes posted like I thought, and I'm just not sure exactly what I want to do with that idea yet. But one of the things I think I'm pretty sure that I do want to do is just keep doing what we're doing unless it doesn't seem like it's working. I mean, I'm going to give you an assignment, and I'm going to give you more problems than what you will turn in. You will turn in just a few, and understand the reason why I'm doing that is multifold. It's mostly for me. I just don't have the time to grade 17 papers came in. I don't have that much time in my schedule. I'm not allocated, by the fact that I'm not getting compensated hardly at all for doing this. But I want you to still feel like you're learning stuff, and so you have the full solutions. Now, one thing I could do, which I was investigating the last time I taught the course, I would put partial solutions up for all the problems that weren't being turned in before the due date. Like some of you have turned in set number 2, I could put up like immediately today, but then it's more work for me processing and producing documents. I have to strip stuff out, because my solutions right now are mostly written from past years teaching that have all the problems in there. I might change problems up and then I change the solutions up. So I'm not sure about that either. But one of the things I am moving towards and looking at how to get more digital communications in here is that reducing the amount of review material that I'm going to have in the homework. Like this next assignment is going to be a lot of new material, so we definitely have to be doing the autocorrelation and power spectral density related stuff, some important theory that's going to come out today. But then next week's, the next one was a lot of review of linear systems theory, filters, some other somewhat new things, but things you've seen before. So I'm spent a bunch of time yesterday night just trying to look at how can I compress this down or get rid of certain stuff to make sure we can get into chapter 3 faster, but not leave out anything that's really important. Now, the problem is you don't know necessarily the difference, but one of the things that I want to accomplish by compressing too is not, number one, bore you with saying I already did this in 3205, and it was either too hard or it was hard enough, but why should I get it again? I'll make a comment on that in a second. And then just keep us moving faster. So why should you do it again? When I first started teaching this class, Dr. Zemer, he was my dissertation advisor in Missouri, at Missouri S&T. He told me that when you teach signals and systems to students, it's like putting coats of paint on your brain. I mean, that was kind of the way that was my interpretation of what he said. It says you need to see it once, like in 2610, where you're first seeing signals and systems when you're still in calculus, right? Your brain, you're pretty weak at that point, but you get your first coat of paint then, and it absorbs into your brain a certain amount, and it's activated at that point. But then you go on and do more circuits, you finish calculus, differential equations, and now you're stronger in math. And then you come and do 3205, which I think Dr. Trimboli has always had a reputation for being very intense in that class. So that's like your second coat, or maybe your first serious coat, I don't know. But he said you need 3 coats. So the third coat to seep into your brain was the signals and systems that communications and signal processing people use. So that's why the book has all this stuff interwoven with new material. And I'll make comments as we go along today, but I've always been trying, and even a PhD guy who used to teach at UTEP. Does everybody know what UTEP is? He used to teach at UTEP, University of Texas, El Paso, right? And he decided to leave teaching and work for ARCA, where I'm working right now. But he said, so are you going to get into digital communications? Because he used to teach the 2-semester sequence. And I said, I'm going to try to do as much as I can. And that's always been the dream, that we would have a strong enough, like 3205 and so on, that we could just buzz faster and get to the new stuff. So I'm going to try to invoke that. Please make comments to me, though, if you say I shouldn't be doing it. I want to kind of, get a good balance going. And of course, I'm also trying to feed the lab, too, in terms of what you're doing in the lab right now. And the stuff I'm going to do today is vital for what you're also doing in the lab. Okay, so what's new on the website? Nothing other than just updates. I did put out the hints page. Like I already said, I graded some papers already. I updated this document yesterday. So now, rather than Miniconda from Anaconda, I put in a discussion on getting set up with MiniForge, because that doesn't have any licensing requirements. When you guys signed up for Miniconda from Anaconda, you had to look at some licensing stuff, right? And maybe even agree to something, even though you're students and you're using it for education. My boss where I work wants to have his system set up with the tools like I'm using, and I said, I'll help you, but I don't think you can. The new version of Anaconda requires stuff that probably the work environment you can't do, just because they're trying to make you pay, and you don't have to pay if you do it the right way. So MiniForge is what I put on my newest MacBook last spring, because I thought they had totally turned over, I wouldn't say to the dark side, but they're wanting to try to make money, because they're putting effort into it. The main thing is you have an environment, you have a base environment, and we all have that. You can build on that with new virtual environments, and that's really vital. So we have that. I will look a little bit at this this document. I'll get it opened up right now, because this was for creating Julia and Jupyter together, Julia and Python, but I did put a section in this on setting up and using VS Code. So I'm going to be showing you VS Code today, and this looks kind of small, so I guess you should make it bigger. When you install VS Code, you put in what are called extensions. So this is a good picture that's in this document of the extensions that I put on my system, but I'm going to show you when I run it here in a bit that you don't need all of these extensions right away, but probably most of them are the ones you'll use. You won't use Pluto, for example, but you'll use Python, Jupyter, a PDF viewer, and then you might want to do a markdown converter, but types kind of takes that over. But this section of the document talks about generating homework and using VS Code to get PDFs of composed. So on to the notes for right now. As we were going through Fourier transform theorems last time, I skipped over this example of rectangular pulse convolution, and then I had another one. I want to just put this up here for a bit, and this is like the classical foundation when you first do a convolution integral. Do you remember it from 3205 and maybe earlier? Convolve two rectangles together, and in the case of they're the equal base width rectangles, you get a triangle. That should be kind of burned in your brain. Is it? So I don't really want to go over it, but if you need to refer to the tedious nature of doing convolution integrals where you slide one past the other, set up limits, and then eventually get a piecewise solution. So this one has a case 1, no overlap, case 2, partial overlap from the left side. Case 3 is partial overlap from the right side. And there would be normally a case between 2 and 3 if it's two waveforms or signals that overlap for a time. They stay one covering the other. That would have created another situation. But in this case, that doesn't exist. And then case 4 when it's slid off to the side. So whenever you do a convolution problem, you always have the individual solutions that you get out of it. And like I said, there would have been in a real scenario, I mean a more typical scenario, there would have been, I get this guy going. Right where that green line is, there would have been another solution in the midst there where they were where there was total overlap, and then you would have been working through that case. And then what you always do with the convolution formulation is you're then reassembling it. In this case, it reassembles into a triangle function, and it gets down to this fundamental result, which is also presumably kind of burned in your brain to just say that convolve two rectangles and you get a triangle. You convolve two width rectangles, you get what pulse shape do you get for that? What memories in your brain exist to tell you what that is? If it's a triangle, if they're equal width, what do you get when they're not equal width? It's a geometrical shape. What?
A rectangle?
No. You're always going to get smoothness. That's another thing. Whenever you convolve, sharp edges go away and you get something that's smoother. But what's a geometrical shape that's a classic from way back, K through 12? A what? No? Trapezoid. Remember, it's a trapezoid would be one side is longer than the other, and then you're going to have sloping up. So you get a trapezoid. Convolve two triangles. Then from probability theory, you learn that if you're convolving density functions in probability theory, you get something called the central limit theorem. So what happens if you convolve enough different pulses, all of similar width but not identical necessarily? It eventually turns into a Gaussian shape. The Gaussian function. That's another kind of tendency that you load into your brain if you keep doing this stuff. You guys were talking about power systems, I think, earlier. I didn't do anything in power systems. I had to take maybe a lab in my freshman general EE class. Power systems to me is almost a totally different animal if you look at the way the industry works. If you're interested in it, though, go for it. I mean, because it's a very stable job. It's almost like being a civil engineer. You're working in the civil area of the community. You work for the, Colorado Springs Utilities. But they have communication systems. They have their fiber optic networks, so they have comms people too. They actually have a whole group here in Colorado Springs that does the comms part of things as opposed to the power systems types. But what you do in those two areas is like, to me, is almost black and white. It's like you're doing one thing. And they would say, we're more important than any of this stuff because if you don't have power, you can't do anything. And I think they're right. And I think, I was telling you how I went to schools of mines for my BS, MS, Michigan Tech, and then Missouri S&T for my PhD. The power systems programs there were really the backbone of electrical engineering when they started, because what did mining need? It needed power. It needed power lines, elevators, all this other stuff that had to go down into the mine. So that was the beginning of electrical engineering, really, I think. So it's pretty authentic. There's no doubt about that. So another example, though, that I want to go through that's in here that I skipped over in getting to that example is just show you that if we want to, well, no, it's in the Jupyter Notebook. Forgot where it was at. Just about how we would use tools, though, and how we would do a Fourier transform. This is just not in the notes, but it is in the sample Chapter 2 notebook. So how do we start to use the theorems and the lookups? And that will take me back momentarily over to here to say, what is it that you have in course materials that as you're working any problems from here on out, you have your formula sheet. So we were drilling a little bit on periodic signals. We're going to get back into that. Chapter 2, or Chapter 3, I mean, when we get into the COM theory, the trig identities are going to start flying around a lot more. We haven't really bumped into them. You haven't had to refresh your memory, but we're going to be looking at this a lot, and you're going to say, why do I have to do that? It's going to become second nature. You're going to remember the trig identity. You might say, you know, these three right in here might be the ones that you think of more than any others once we get into the modulation theory stuff. So you think, what do I have? I've got cosine times cosine, sine times sine, and then the mixed one in between, sine times cosine. Do I have them roughly committed to memory? Yes, but the more you use anything, pretty soon it's locked back in. But don't hesitate to look at this sheet. What we're looking at right now, though, is we already established last time this first trig identity, or this first Fourier transform pair. Rectangle goes to sinc in the frequency domain, and then the dual of that is rectangle and frequency becomes a sinc in the time domain. These get used an awful lot from here on out, especially in the COM chapters 3 and 4. We just talked about how a rectangle convolved with a rectangle gives a sinc, or gives a triangle, and that becomes a sinc squared. And that makes sense once you recognize the convolution theorem, and that's down here, recognizing that if you convolve two signals, you get the product of their Fourier transform. So naturally, that's where the sinc squared comes from, right? Because a rectangle becomes a sinc, and another one is another sinc, and then they're multiplied together. We also used these theorems, time delay and frequency translation and modulation, an awful lot. I mean, I'd say myself, only because this is what I do all the time, this one is probably the backbone of almost everything we do in communications theory. And starting in lab 3, this will become fundamental, because those of you in the lab will be actually mixing or multiplying signals together, and you'll be thinking, I get all this spectral information coming up on the analyzer. How are these things related? And it comes about from the mathematics here, where we get a spectrum shifted up in frequency and then a spectrum shifted down in frequency. So what I wanted to look at with this example, though, which is in the notebook only, it's not in the notes, is, oops, I didn't want to do that. Yeah, I wanted to do that. Just clicked on the wrong tab. So this is an example of a simple application of the Fourier transform theory, both transform pairs and theorems. So here we have two things that jump off the page. Number one, we have a superposition of two different pulses, and this is just a no-brainer. You know that if you're going to Fourier transform that, you can do it term by term and then bring it together with appropriate scale factors. Nobody has a problem with that, I'm sure. Then how do we break down each of those transforms? We say, okay, each one of these is a rectangle, so it's going to be a sinc function in the frequency domain. But the nuance is that we have a time shift going on in different directions in each of these. So the way I chose to work this problem was I just said, okay, I know there's a common sinc F because they both have, oops, I need to turn this, I'm in the notebook, I can't draw on it. Never mind. The common pulse width, though, of 1 means that I can pull out sinc of f, f times tau, tau is 1 in this case. So sinc f factors out, but then I get an exponential phase shift factor with a positive sign because I'm shifting it to the left, and then I get a negative sign because I'm shifting it to the right when I take t minus 1/2. Those two are sitting there, factored out, and then the logical thing that you always think about in signals is Euler's identity and variations on that, right? That's just commonplace. So the setup here is it looks like a sine because we have an e to the x minus e to the minus x, and that's our setup for sine. So we know we have to put a 2j in the denominator, and then a 2j just pops out in front. So pretty straightforward, right? This is something that, even though it's review, because it's related to the shapes that we use in comp theory, could show up on the exam. Something along these lines. And how you would work this problem is you would, of course, practice and rehearse by looking at homework problems and old exams, but you'll also have your crib sheet. Don't leave it to chance, right? Just double check, plug into the right tables. In this case, I went ahead and just plotted the spectrum. So I plotted the time domain function in Python, and then I also plotted capital X1 by just taking what's in the math up here and just coding it directly. So there's nothing too exciting about this in terms of using a numerical method, but I'm just using here Python to plot it. So there's the spectrum. It's a pulse up and a pulse down, and there's a waveform type that we use in digital communications, which fundamentally each digital bit gets transmitted in this scheme, and it's talked about in Lab 2. It's near the very end. It's called Manchester encoding, a Manchester encoded pulse shape. And I think I opened this up over here. Yeah, Lab 2. So when Lab 2 is looked at, and I'm doing this for the benefit of those that are in the lab, I have a section in here called line coding, I think. Maybe I have right here. This comes from a later chapter in the book. It comes from chapter 5. But the standard digital encoding, which naturally falls out from digital logic, would be hold it high for the entire bit period, hold it low for the 0, let's say. And then in digital comms, we generally make a 0 and a 1 be a 1 and a minus 1. So we're sending a waveform that takes on polarity. It's bipolar. But another type of signaling, besides these others in between, is split phase. And what split phase is doing is it's sending, for each bit, it's sending half the bit period is high and half the bit period is low. And that's exactly what we just saw over here in the notebook. So I'm telling you this because it's not obvious that this looks like an academic problem, but actually it has a basis for something, and so I can tell a story about it. Why would we want to do this? There's pros and cons to it. I'm curious, does anybody notice anything distinctive about either what's going on in the time domain or the frequency domain that seems remarkable? I'm thinking about passing a signal from point A to point B. I'll just give you some hints then. So the pulses are half the width of a bit, let's say, in the time domain. That means the pulses are shorter in length, which means the spectrum, because it's the sinc function, the lobes are going to fall. The first nulls in the lobing structure here are going to be twice as far apart, which means it occupies more bandwidth. What do we care about occupying bandwidth? Well, we want to be conservative. We want to get as many bits per second per hertz of bandwidth through our pipe. So downside there. But somebody created this idea and they were motivated to do it. So what's another thing you see in here? When you look either in the time domain, you can say the average is always 0, for whether it's a plus, for whether I'm sending a 0 or a 1. So think of this as being sending a 1, and then I would invert this waveform if I was sending a 0. The average value is 0, and in the frequency domain over here, that means there's a null right here at 0. There's no DC in this waveform. What opportunity does that give you? I'm thinking maybe now of a twisted pair or someplace where you don't want to have the ability to pass DC. It's better to do something with a transformer for isolation and coupling. I realize we were talking about power systems. Power systems uses transformers, but other signal processing systems definitely use transformers, but not in the power system sense, but just coupling without a DC required. So that's what's nice about this. There's no DC, the spectrum goes to 0, and it's not sensitive to a bias. It's always going to center itself right on 0. The average value is 0. And then a third thing about this, which is really vital, because we'll see eventually when we're talking about coherent communications more, that you need to have knowledge of the edge. Where does that transition occur? So you need to have what's called a bit or symbol synchronizer. You need to be able to synchronize so you can make bit decisions at the other end. And now I'm going to take you on a little side thought about digital logic. What is your favorite type of flip-flop, let's say, from digital logic days? Which one do you like the most, or do you have any favorites? I mean, there's multiple types, right? There's JK, RS, D. What are the other letters? I don't remember. I used to teach that, I used to teach electronics at one time. My favorite is the D flip-flop, because it's very centric to digital communication. So a waveform comes at you from a distance. What's the first thing that you want to do to get knowledge of your clock edge back again? You might so-called retime the signal, and that's what a D flip-flop is for. A waveform can come at you. You have a clock running underneath it, and you're going to clock it through a D flip-flop, and then that reestablishes the timing edge on it. Is that what you were taught? I mean, I don't know what they tell you anymore, but do you remember that's a use of the D flip-flop? Okay. Well, I'm telling you it's a use. I mean, it happens in our lives, actually, too. Think about traffic signals and the flow of your car down the highway. What is the effect of a traffic light, which is synchronized by the Master Control Center in Colorado Springs and monitors the cameras, and they can actually change the timing on the lights? Does everybody know that? They change between morning and evening when people are going one way or the other way. But so that's like the action of a D flip-flop. You're retiming the traffic, the packets that are flowing through the network. So people speed past you and you say, where are you going? This light's going to be down at the next intersection because we're getting retimed there, and we're going to all group together again no matter what. So at any rate, the thing about the edge in the Manchester encoding is a phase lock loop that needs to look for transitions on a regular basis. There's always going to be a transition with the Manchester encoding. It's either going to be from high to low or low to high, but it's always occurring every bit. Whereas in a non-return to zero data stream, you could have a long string of ones or a long string of zeros, and if it goes on for too long a period of time, you kind of lose track of where's my edge, because I don't see it in the data alone. And generally in data communications, you don't want to send a separate line of clock. You want to just regenerate at the receive end. I don't know if that has ever entered your mind, but in your senior design projects, you might be doing things with retiming or latching and things of that sort. It's cool. In my mind, I like communications and signal processing, but it brings facets from every other area, except maybe power systems. I don't know. Yeah, power supplies are important. When I worked on my projects, somebody had to be in charge of the power supply and the regulators and the buck boost and all that stuff that we now have. That's some really fascinating stuff that's happened over all my years. The fact that we can start with a single supply, and now we can produce two supplies because we can create, through a buck boost converter, we can create a variety of supplies and different polarities if we want to. Does that ever, you ever think about that? That's basic electronics, I guess. How many supplies do you want to have? That sort of thing. So those are some thoughts just from that example. The modulation theorem, this is just an example in the Jupyter Notebook from that, where I just said, okay, modulation theorem is very straightforward. We'll be using this extensively in Chapter 3. Just multiply any signal times a cosine of the carrier frequency, and we know from the math that we already looked at last week, we're going to get half the spectrum. We're going to get the spectrum at half amplitude shifted up and then half amplitude shifted down. So, and that's this factor of 1/2. Just put that in Python and run that through. It works wonderfully well, and this being that this is live, I'm just going to change something now. Suppose that I make the carrier frequency 5 rather than 10, and it's thinking, maybe I have to restart this kernel. Yeah, it says kernel unknown, so I think I had to do a restart. So whenever you're working in Jupyter, it can be in the VS Code version of Jupyter, or it can be here in the Jupyter Lab notebook. Just do that. Restart your kernel. I think I had brought this up by restarting this notebook. So now I'm going to have to go back to the top, and I'm going to have to rerun the top cell. But I'm not going to worry so much about running all the cells ahead of it. I'm going to run that top cell, which has got all the startup stuff, loads all the packages that you need. I'm going to go down here. Now I'm going to run this with 10, like it was originally. Minimize this. You know, on my laptop here, I have a small screen, so I have to minimize things like this because it makes it too tiny, too cramped. If you're on a big monitor or something, definitely spread out and use the space. If you have a monitor, bigger one you use at home or something. But this is an interesting facet too. We've shifted the spectrum up and down, but what happens if, you know, I move this down to 2 for my carrier frequency? Now those spectra are starting to come together, and when you're in the lab and you're looking at the spectrum analyzer, which just shows you from 0 hertz up to a positive frequency, you cannot just assume that this spectrum here is not on its own. It's not autonomous to itself, because what happens is if I lower the carrier frequency down even further, you'll see that now they're actually overlapping a little bit. You can't really see it, but what happens is the wiggles that are coming off of each side from the sync squared function in this case, because I'm using a triangle shape, are actually influencing the positive axes. Now, symmetry is maintained between the negative and positive frequencies, but because the carrier has been brought closer, you're going to see that asymmetry just on the positive side. You're not going to see it as an isolated, you're not going to see just this x of f minus f naught. It's going to get some leakage from the x of f plus f naught. And in the lab, I particularly have you see that happen. Most of the time, though, in a communications type situation, the carrier frequency is very large, so the signals are not going to be kind of butting heads right at DC. They're going to be spread way, way apart. They're going to be at megahertz, gigahertz apart. But it's nice to know that the math actually does work. And I think one of the things when you're young and naive is you say negative frequencies, this seems so weird to me. You don't do anything in reality by tuning to a negative frequency on a, say, a radio in a car. or a waveform that you receive from space, but when you're doing signal processing on it, you have to be cognizant of the negative frequency components, and this brings that to light. I mean, I think, again, for those of you in the lab, you'll see it more clearly. I think I actually put some pictures in the lab, though, too. If I go back up here. I guess they're down below. There's an example where I'm doing a pulse train. It's centered at 10 megahertz with the bursts of the RF carrier, but notice it's not symmetrical. And why is that? It's because there's another one of these things sitting off to the left. It's not going to show up on the screen on the spectrum analyzer in the lab, but it does cast a shadow onto the positive side. And you see this wackiness going on. So don't think that it's like somebody messed up the calibration. It's real, and it's part of the math. So, any comments on that? Surprises? It's not aliasing that you think of due to sampling theory. It's just the mathematics of the negative frequency. So I think I've exhausted that example. I did a band-limited signal in here. Next thing we'll be looking at when we get there is the PN sequence. But now I'm going to go back over to this. Actually, I'm going to, since I was just looking at Jupiter, I'm going to look at VS Code for a moment just so I can kind of get that out of my system. And then you can be pondering it. But what we're moving into next is Fourier transforms in the limit. And then this will lead to a nice theorem, and then we'll go into autocorrelation and power spectral density throughout the rest of the lecture. But VS Code, what is it? This is what it looks like when it's up and running on your machine. I have a link to it from the original syllabus, and that's how I recommend if you want to give it a try. You go over here to the syllabus link, and you follow this. Microsoft is extremely proud of everything that it does with Copilot and its AI and all this other stuff. And VS Code is loaded with all kinds of Copilot stuff. And I don't know, does anybody use these tools in your daily use? I mean, I use it a lot in Google when I'm searching. I get the little articles written by Google. I like how it pulls things from all over the place and writes a nice story. When I had my thumb surgery, since I'm a bass trombone player, I was wondering how am I going to start playing again and not hurt myself or re-injure myself in my hand. And I took it to my hand therapist. It wrote a really nice article for me, like when you start playing again, because it merged the medical side with trombone playing and holding all this weight in your hand. And it wrote a really nice story, and I took it to my therapist, because it mentioned your physical therapist or your hand therapist is going to do this and that. And I showed it to her. I said, am I on the right track, and do you agree with these things? Because I said, I didn't write this. AI wrote this. But it wrote a nice story, is all I can say. But I think we're all engineering smart enough to know that it's not perfect, right? It might write a story that's totally false or has some bad things in it. We all have to work that through. But at any rate, VS Code, I've used its AI capabilities a lot. I think over the past year in the project I was working on, I was doing a lot of coding in VS Code for Python. And I let it help me out a lot. And it helped me out so much that I burned up all my execution time from the free version of Copilot. And then it just all of a sudden, one day, it was like, it's not helping me anymore. It's because they wanted me to pay some money. Does everybody find that okay? Somebody has to make money for all this work, so. But it.
A lot of them, they give you a 1-year trial if you give them your student email.
Okay, for you guys. Yeah, I was working for Arcus, so I didn't. I wasn't even sure they wanted me to use it or not, but because it does some scary things. It's like it's trying to predict everything based on my patterns of what I have in my code already. And it sometimes it was just beautiful. It just like, yep, you got this all right. I'll okay it, and I'll say go with it. Other times it would just start going off on a tangent and writing a bunch of stuff that is like, no, I'm not trying to do this. You're going off, trying to make me do something else, and I had to, stop hitting tab or whatever to let it do a code completion. But it's very easy to download and install. So once you get it up on your system, you will have this kind of environment that is traditional integrated development environment for coding. And it has the sidebar, which I traditionally keep on the left, and then it has the main screen. But you can do all the other types of things you want to. Like you can drag that tab and you can say put it at the bottom, put it at the right, just leave it where it is. So you get all this environment stuff. You can look at the file twice, so you could have different sections of code. You can do that stuff in Jupyter Lab too. You probably haven't tried it, but you can take a tab in Jupyter Lab and you can hold the left mouse button down and then drag it around over the screen, so you can break your screen up into multiple views or multiple parts of the screen. So the first thing you do when you get it installed is you want to put some extensions in. And the extensions, and this was the question I got asked last week. I forget your first name. Alan, right? Yeah. You asked me about VS Code and why do we still need to have Python and a base and everything. So everything that we did with installing Miniconda sits behind the scenes. It is still our base of Python and modules or packages that we install and we gain advantage on. So what you have to do, though, is you have to take VS Code and put an extension in, and that's what this little block icon over here is. It's installing extensions. So the extensions I put in was Jupyter Notebook support. It installs a bunch of other things, but it installs that. It'll install all these other things all at the same time. And it's probably best to just let it do that because they're all pretty much related to each other. It's important to note that even though I like it and people I work with like it a lot and use it a lot, notice how many stars it has. It's got a very mixed review. It's not like some of the reviews you see where people are just, yay, it's great, fantastic. People are highly critical of Microsoft because, I don't know, does anybody have a thought on Microsoft, the empire? Apple has their empire, I mean Google empire, but people, I think, hold them to a very high standard and they don't want to see them selling stuff always. And VS Code is free, but I think they're just hypercritical of it. It works much better than it did when it first came out, the Jupyter Lab part of it. So you want to get Jupyter Lab installed, but then you also want to install the extension, the Python extension. So this one is vital. It'll give you all of the nice coding features that you want, code completion, code highlighting, and other things that automate design. And I'm going to show you a bit of this because some of you are going to say, oh, I like this so much better than Jupyter Lab. But you're going to have to decide. I'll go back and forth. I'll use one for a while, and then I decide I like the other one better again, and then I just have them both available.
You use them for the lab report.
VS Code?
The Python extension, Jupyter Lab.
Jupyter Lab is what you installed the Jupyter Lab in your virtual environment, right? Yeah, Jupyter Lab is this guy right here, right? I gave you Jupyter Notebooks, but you can open Jupyter Notebooks in VS Code. And some of you might decide to switch and start using VS Code.
I just installed it on my computer, that's all.
What, you put what?
I just put it on my computer, that was it.
Jupyter Lab, right?
Yes.
Yeah. If you want to switch and use VS Code, it gives you similar capabilities, but not the same. They're just slightly different. And I'm just giving you a quick little overview. So you put the Python extension in the Python debugger. So one of the things I like about VS Code, and this depends upon your how you've grown up in your microcontroller experiences in your courses at UCCS. Were you taught always to learn how to use a debugger? True? False? I was not a debugger user, but my wife is a programmer. I mean, she was a developer, and she taught me right after we got married. She said, she didn't tell me anything about how to do my work as an engineer. She's also an engineer, but not practicing chemical engineer. But she said, learn how to use a debugger. So I tried it out, and ever since then, it's like I want to use a debugger because it has a lot of advantages, especially when the going gets tough. So the debugger that's available in VS Code for Python, for C and C++ is just really, really good. I like using it a lot. So you definitely want to use the debugger, and I'm going to show you how easy it is to use it. There's a lot of other extensions out there. You just search for them, and they're always trying to push more stuff on you. Recommendations always show up down here, just depending upon what you're doing and what the AI is doing. It's always trying to say, oh, I think you should have this one. Oh, I think you should have this extension. There's just a lot of them out there. But VS Code PDF Viewer is very nice, so I have that one on. So this pane lets you see your files, and I'm going to close these two, but suppose I'm in a notebook. So I opened up a notebook, or Control-Shift-P brings you up a bunch of commands you can have listed at the top. So it might be, if I type JU, it's gonna pull up immediately with something to help me with Jupyter, like create a new Jupyter notebook. So it has a lot of features like that. But as soon as I opened up an existing Jupyter notebook, the first thing it says over here is you need to have a kernel running, and this is the stuff that you installed with your virtual environment. Jupyter Lab in the browser does it automatically, but over here you have to click, and then it will say what other kernels do you have available on your system. So it's going to go trying to find any and everything that's on your machine, and I have various kernels on here, but I'm particularly was looking for Python environments. I have some installed for Julia. I have the base version that we put in with Miniconda, but I wanted to get to the kernel that has all the other packages for Python in it. And for those of us that followed the directions that I gave you, it's going to be DSP-COM 313. Remember the virtual environment I asked you to create? So I select that one, and now that's going to be the basis for my running my notebook. And I can restart the notebook just like I did over in the Jupyter notebook. So I'll restart it. It has different things that it shows up down here. And now that it's restarted, I can run my start cell. It's still a Shift-Enter, and it runs that first cell, and it puts a little green checkbox down there to just say, yep, I've run that already, it's done. You can add a code cell or a markdown cell. You can delete, you can move them up and down, you can drag them around, just like you can in Jupyter Lab. And now it's got generative AI stuff thrown everywhere. So watch out for this stuff, because it might take over your editing. I mean, it's going to always say, ask you to OK stuff, but it's very much tied up in the VS Code environment. So here's a code cell that I might run, and this is just like we have in the other sample notebook. As a matter of fact, I could go over, because I can see I'm in my notebooks folder. I could open this up right now. This looks just like it does over in Jupyter Lab, and I haven't done anything awful like ruin the file that Jupyter Lab can't work with it. They can actually both have it open, and if you edit it in one environment, it will show up as an update to the other, and vice versa. But notice when you first open something up, it'll have an italic look to it, and then if you really want to open it, you double click on this like that. It becomes straight up and down text, but it's still saying I have to give it a kernel and start using it if I want to do my Jupyter work in VS Code. I'm not going to go with it right now. I'm just going to leave that one alone. But I'm going to just show you how the debugger works and how convenient and nice it is. So if you hover over on the left side of your code window, you see the little red dots. This is going to set breakpoints. So I'll just say, I'll set a breakpoint there, and I also get a code outline over here too. And this notebook only has one markdown cell that has a header in it. And if I double click on it, just like in Jupyter Lab, or close the cell back up again, that's the one that's showing up in my outline. Once I start debugging though, then I will get more breakpoint, a debugger window, or I'll get a listing of breakpoints I've created. But how easy is it, let's say, to take this cell of code, which is acting up. It's got something in this cell. When you run it, it gives you an error message. Has anybody not had an error when they're typing in Jupyter? Everybody's had it happen, right? And you get better and better at it the more you look at it. You typically look to the bottom of the errors and then work backwards to see where they are. But you develop a skill. But here what we can do is say, I want to run this cell because I know it's messing up down in here and I don't know what I've done. So you can click right here and you can just simply say, I want to debug this cell. And it will automatically, it just started the debugger. Here's all the variables in my workspace, call stack. Here's breakpoints that I've created, and all kinds of other support tools. And then here's sort of the main command environment, which can be moved around. But this is just like a debugger you'd see for a microcontroller or anything else. I can run or continue. I can step over. Or I can step into. So I'm just going to say right now I've already come down here, and I can see that A is going to run through this point, and so I'll just step beyond it. And so A, I can hover over any variables, and I can look at arrays. And then if you go Control backtick, you will open up a terminal window. And the terminal window gives you a PowerShell environment, but it also gives you the debug console. And then you can just say, well, what's the value of F naught? And just enter that in, and there it is. T here is an array, so I have access to that. It just tells me what the array is, but by default it's also giving me some values right up here next to it, shaded out. And then if you hover over it, you can actually drill into it in more depth if you want to. And then you can continue to step down through this. And then finally, if I just get tired of stepping and I have resolved my problem, I just finish it off, and then it's done. It produced the plot right in the window. You can do other things like save your plots out, save it as a PDF or whatever. I mean, things very similar to what you can do in Jupyter Lab, just somewhat different organization. Nobody's used VS Code a lot already in this class. I'm just curious, because I've had people come in the classes before and say, I'm using VS Code, I've been using it for a long time, can I use it? I said, sure, if you want to use it, you've got your choices. So what else was I going to show you? We were in the debug screen. We can turn that off. We can globally search our entire folder for pretty much anything and everything and get links into code in an entire folder. If that's a curiosity, like I lost track of something and need some help. But you can also just search locally within the file by doing Control F. So, and it will tell you how many instances, like I created px from the output of this PSD function, and then I can just roll down through all the other places I use the same variable. When I created this more in what I call Pythonic, and this is a term that I had to learn a long time ago. Pythonic, it's like it's an organization. Python coders, and they will complain about people that don't follow conventions of Python language. So they say it's not Pythonic, or they say it's Pythonic. So I'm teaching you sort of a sloppy way of coding because I want to make this an easier on-ramp from MATLAB. So I import all the functions from NumPy, I import all the functions from Matplotlib, PyPlot, and I just force you to use the labels in front of the dot for the various packages, to at least keep them isolated in what we call the namespace. But a more formal way of doing this is to just import NumPy as NP, import Matplotlib PyPlot as PLT, and then kind of follow in this tradition where you actually have to precede everything by the namespace that you created for that package. PLT is the alias for it, and then when you get to the very end of this plot, you can't just let it do its thing by itself. You actually have to say plot show, or this plot GCA is another way of getting it. In the Marimo notebooks that I haven't shown you yet, you want to use the .gca. So what's the moral of this story regarding the use of tools? You were very laid back in MATLAB. You didn't have to hardly take that much interest in coding. But now, as you move into Python, you realize there's more things you have to do. Has everybody kind of noticed that? You just can't be a lazy loaf. But the thing is, there's so much coding that engineers do these days that it's just kind of been a natural growth. And you're young, so don't stay back in the dark ages. You have to be up with, what is the way people work. And so the coding side of things tends to be more and more present all the time. And the tools help us stay kind of in lockstep so that we can create things and share them and have things more standardized. I still like to minimize the typing. What I find is true is that more and more typing, but VS Code has this advantage going for you. Suppose I forgot to put PLT in front of subplot, knowing that subplot is something that goes along with Matplotlib graphics library. Or suppose, and this is really tedious, but suppose I wanted to just use PI for pi and not precede it with numpy's .py. What does VS Code do? It puts little squiggles underneath any variable that it doesn't know about. And right now it's telling me, hey, if you run this, it's going to beat me over the head and say, pi is not defined. Oh, I didn't realize that. Okay, so you go back up here and see, oh yeah, there's a squiggle in here that I should have resolved early on. So I put the NP in there and the dot, and of course it's telling me all the other things that are in the NP library. Okay, so I'm good to go. So I might go Control S and save it. And now it's zapping me again. I didn't take care of subplot. I didn't put a PLT in front of it. And it goes on and on from there, but at least this tool it's not typing it for you, but this is what the AI part will try to do in VS Code. It will try to make the suggestions. Once you start typing a new line, like if I was to start typing y equals, it's not giving me any suggestions right now, but the more code I have open and the more times I've used it, because I just put this on yesterday, it's going to be trying to second guess me and tell me what I want. Jupyter Lab doesn't do that, but VS Code will. So I'm just letting you know, and you do have choices. So I'll leave that alone, and I'm going to go back to the math stuff now. Any comments? Any initial reactions? It's pretty nice, though, that you have your choices, and everything roots in the way I started you. So I started you with what I think is the foundation is you need to have a Python. You have the base Python that we have available. And then we have the other additions to it, virtual environments that we create. There's a lot of different virtual environment managers out there too, so Python has got just so many different things with it. I'm just setting you on a track, and then you can jump and change to something else. You'll say, this was no good, I learned this in the beginning, now I want to do something else. I'm fine, I'm perfectly okay with that, because you have to be yourself, but I'm just trying to get you started with something. The virtual environment idea, though, still pays for itself in the long run, because this is what I'm running to run Jupyter Lab when I launched it from the terminal. This was for creating a Marimo notebook, which I may show you later today. I ran Marimo edit and brought up another notebook, and both of these tabs correspond to different virtual environments. This one is my Marimo virtual environment, and this one was started a long time ago from wherever I started it. Not there. No, I guess this is Marimo too. The other one's running from, I don't even know where it's running from anymore. I lost track of it. Sometimes in your terminal, things disappear and you're wondering, how am I still running things? And sometimes I have to restart stuff because something dies in the terminal and you're actually still running something. You don't even know how it's still running. And I actually didn't check that, so I may have to restart something because something may crash at any moment. So now what we want to do is go back to some math, and this is going to be very powerful stuff. We're going to first get on the bandwagon. Remember from weeks ago I said we would take the Fourier series, which exists for periodic waveforms, and we'd get those ideas all merged under one umbrella of the Fourier transform. So the first step in that direction is Fourier transforms in the limit. So the motivation is we have periodic power signals which have line spectra always, and those line spectra came from the Fourier coefficients. And I was trying to refresh your memory ever since the beginning of the semester, and I'm going back to my memory saying nobody ever really liked Fourier series a whole lot. It just seemed like very messy stuff that was tedious for each waveform. Fourier transforms seem more pleasant. I realized Laplace transform is probably the most pleasant, working in the S domain versus the frequency domain. But we are forced to be in the frequency domain because that's the core of communications theory. So we have periodic power signals, but then we have non-periodic or aperiodic energy signals, which have this nice Fourier transform relationship. We have the table, we have the theorems. Can we unify this? So what we have to do is you have to go over to here and you say, we're going to allow impulses in the frequency domain. This is not going to be the same original definition of Fourier transform as an integral, because we have to be careful when we're working with delta functions. But we can do it, and the basic concept is Fourier transform in the limit. The book talks about this. So one of the things that's going to happen, we already saw the energy spectral density last week for an energy signal. So that's going to eventually lead to saying if we want to have a spectrum like an energy spectral density for a power signal, it's going to be the power spectral density if it's a power signal. And those are the signals that we're essentially always dealing with in the lab. When you're dealing with a function generator generating a waveform, if it's a noise signal coming at us from thermal noise, it's going to be a power signal, and we're going to want to get its spectral representation in terms of the power spectral density. So we're going to get there eventually before we leave class today, but right now let's go back to motivating the Fourier transform in the limit. So suppose we have a constant signal A, and I guess I'm going to change the color here. So right off the bat, this signal is definitely not finite energy, right? A DC coming off of a battery, constant. We model it from over the entire time axis. There's so much power associated with the signal. It's A squared, right? If you had a 1 ohm system, it'd be A squared over the impedance that it's across for in circuit theory representation, but we're assuming a 1 ohm system. So now, how do we take the Fourier transform of the constant? We're going to approximate this constant with a rectangular pulse that has amplitude A and has pulse width T, and then we're going to take the limit of it as T goes to infinity. So remember, the idea here is Fourier transform in the limit. So this is the limit that I'm talking about. We're going to start with a small pulse. We're going to let it just go over the entire time axis. Everybody good with that? I think engineers, we like this. Mathematicians worry about every little thing, and we try not to crash with math that doesn't work, physically. But we're guided by physics. We want something to physically make sense to us, and our math models are convenience things. We want to have a nice set of tools in the math domain that work in practice. So we Fourier transform this, and the idea of Fourier transform in the limit is this is going to not be inside the Fourier transform operator. And this is where the mathematician side of things would say, oh, we have to be really careful here. If we interchange the order of limit in a Fourier integral, are we going to get something inconsistent going on? So we have to do this carefully. But we're doing it for signals that are physically representable, and the math models are acceptable for engineering purposes. So what I'm going to do, I'm just observing when I say note that, take the Fourier transform just of the A rect T over cap T, and that's AT sinc FT, standard transform for a rectangular pulse. Now the Fourier transform, the limit idea says let's consider that the limit as t goes to infinity of this approximation to my throat gets dry all the time and I don't swallow enough. It's like when you go to the eye doctor, you don't blink often enough, your eyes are drying out, you need to blink. Does anybody have that problem? Some of us have to use eye drops because we quit blinking and then our eyes get so dry that you close them and it's like, they're creaking at you because they're all crusty feeling. At any rate, my voice has the same problem. So we take the limit as t goes to infinity, and what happens is we start off with a sinc function for t1, and then as t1 gets bigger, say t2 much greater than t1, the spectrum is compressing down. It's wiggling around, but it's getting much narrower and more focused down to a point. So in the limit as t goes to infinity, we can say that that sinc function actually behaves like a sample function for a delta. In other words, it approximates as it shrinks down. This wiggling here is looking more and more like a delta. It's going to shrink down to 0. And yeah, it does have variations above and below the time, the axes, the or the x-axes, but it approximates, it's looking more and more like a delta function. So the Fourier transform, the limit idea then for constant A is just A delta of F. Is that the end of the story? Well, in a nutshell, it is. From this, everything else can be built. And we have to accept this as engineers to say this makes sense to us for our purposes, because our purpose is that it's a constant signal. Where should all the spectral content be located for a constant? Should it be spread at different frequencies, or should it just be focused right at DC?
Right at DC.
Pardon me?
Right at DC.
Yeah, right at DC. if you're a mathematician, you'd say, oh, I have to be really, really, really careful about this, but we're looking at it more pragmatically. We're saying it's an operational math kind of a concept. Focuses, if it's very long, or maybe not very, very long, but still very long, if the width of the pulse is only this long, but I'm sitting right here in the middle, zoomed way, way in, I don't notice the fact that it ends here and ends over there. For all practical purposes, it looks like it goes on for a very long time. So it's all focused at DC. So we get that, and then if we plug this into the inverse Fourier transform, we have the sifting property of the delta function. And I just noticed that I've got an extra f in here. So we let the delta function sift out the functional value at f is equal to 0, and that's just a. So immediately then we can get all excited and come up with a bunch more Fourier transform in the limit pairs. So we could multiply on the time domain side by e to the j 2 pi f naught t. So that's just going to do what the frequency translation theorem does. It just shifts the delta up to f naught, multiplied by cosine, the one in the middle. It's going to be modulation, so it's going to split it amplitude-wise and then push it positive and negative frequencies. And we can also include a phase factor if we have plus theta. And then we can use the duality property, the Fourier transform, and say, oh, if we have this complex sinusoid sitting over here, that inverse transforms back to a time-shifted delta function. Along the way, we observe a fundamental property, which I talked about last week, called the reciprocal spreading property. And I kind of was alluding to this when I was talking about Manchester coding, too, and that is that in the extremes, a signal that has infinite width has, which is the one on the right, has 0 width in the frequency domain, whereas a signal that has 0 width in the time domain has infinite width in the frequency domain. That's the extremes of reciprocal spreading. But with the Manchester pulse I was talking about, you have two half-width pulses, which are half the length of the full-width rectangle in non-return to 0 signaling. The bandwidth is going to be approximately double because of the reciprocal spreading idea. So we about double the bandwidth for the Manchester over the non-return to 0. Those of you in the lab are going to create a Manchester waveform by editing the ARB capability and the generators. You're going to use an Excel file or a CSV file to create the Manchester pulse shape. I just remembered that because I was studying the lab. This stuff is, thank you, it's all interconnected. It's about time for our break, I guess. So what we can do now, and I'm going to finish this, and then we'll come back, and I'll let you ponder this while you're walking around getting something to eat or drink. How does this bear on Fourier transforms of periodic signals? We have this top equation which says we can expand some periodic waveform in terms of Fourier coefficients xn, but now what can we do? We could Fourier transform this whole thing. So we come down here and just blindly say it has a Fourier transform. And then we take our Fourier transform in the limit ID and say we can Fourier transform this term by term. But that's going to consist of some constants, x of n, and e to the j 2 pi n f naught, which is just going to be delta functions in the frequency domain when we Fourier transform that. So we're seeing immediately that for a periodic waveform, we can just get its spectrum from the very last line, or if I try to rearrange this slightly, just get its Fourier series coefficient and use it to weight the spectral lines. Now you're saying, wait a minute, I have to get that Fourier coefficient to make this work. You're saying you're not telling me the straight story. How do I do this if I don't know the Fourier coefficient? Well, there's an answer for that, and this is the big, to me, this is like probably the most revolutionary thing for today's lecture is how wonderful this little theorem is. I didn't appreciate it until I started teaching the class. Dr. Zemer kind of raved about it as being, you know, the greatest thing. You know, people say the greatest thing since sliced bread, for example, or whatever your favorite cute saying is. So this is what's coming here next. So before we go the rest of the way, though, and get the theorem, what's the difference between a line spectra and continuous spectra? There's really none. We have a line spectra, and from it we can sum phasors, get back to the time domain. That's what the Fourier series tells us to do. If we have a continuous spectra, we convert it to the time domain by integrating the impulses in the frequency domain through the inverse Fourier transform, and we get the phasors that way. So there's really it's all the same thing. It's just how you look at it, and I prefer the bottom because we can leverage the power of the Fourier transform and only really concentrate on that as our main frequency domain conversion tool. So before we go to the end, we have to develop the ideal sampling waveform, which I think you saw somewhere. I think it might be in 2610. I'm not sure if it's in 3205. You remember the spectrum of a impulse train? This waveform here, this sampling waveform. It's okay to say I don't remember, but I honestly don't know if it's in 3205 or not. I'm just telling you we now have this, and we can say it's periodic. So the way the book gets to it is, let's just pretend that since it's periodic, we're going to go for its Fourier coefficient. Let that be y of n. This is our integral, but the waveform is delta. So the coefficient is just very simply 1 over fs for this pulse train. And what that tells us then is that the spectrum of the pulse train is fs, which is 1 over ts, fs being the sampling rate, times delta of f minus nfs. So this Fourier transform result now, which we got sort of standing on Fourier series briefly, just tells us that we have, at the top in the blue, we have a pulse train, ideal periodic signal with idealized delta functions, and then in the frequency domain we get delta function sequence. So this is trivia, only that engineers in signal processing appreciate. It's like a quiz question. What signal, this is kind of an off to the side thing, but it might help you remember this. How many signals have the same transform, have the same form in the time domain as they do in the frequency domain? So this tells us that an impulse train has an impulse train in the frequency domain. What other signal? This used to be a trick question when I was first teaching this class back at Missouri S&T when I was getting my doctorate. Some professor said, it might have been Dr. Zemer, it might have been somebody else, saying, you know, answer this question. What are 3 signals that have this property? So here's one. Can you think of 2 others? And one of them's really silly. You watch Jeopardy. I mean, anything where you have these quiz show type things where you have to come up with what are the other ones. So Fourier transform of 0 is 0, so that counts as one of the 3. The third one is a Gaussian-shaped pulse, a bell-shaped curve. In the time domain will become a Gaussian spectrum in the frequency domain. Had you ever seen that before? Okay, trivia, right? It's cool though. So this is the one that's the focus though, the impulse train. And this is idealized. We can't really generate perfect deltas, but it represents conveniently in sampling theory. We use this to represent the action of taking samples of an analog waveform and getting it into a discrete time waveform. That much you saw in 2610, I'm pretty sure. It got introduced or talked about there. But the Fourier transform really wasn't talked about much because you weren't finished with calculus yet when you were taking 2610. So we can bring that together now to form this, what I'm calling famous theorem, and here it is right here. We expand any waveform that's periodic by convolving the fundamental pulse shape P of t with an impulse train. So this replicates the waveform up and down the time axis with the individual periods. I'm thinking of like a pulse train where you have all the pulses, or it could be a burst of carrier frequency, which you explore in the lab. But this does it using the idea of the convolution with the delta function replicates the function, and it takes into account whatever the argument of the delta is. This guy just maps through from the sifting property the delta function. So now we Fourier transform that, and we end up seeing that because we can break, we have the convolution theorem and Fourier transforms. If I'm convolving two signals together in the frequency domain, I'm multiplying. So here's the multiplication. So I have the Fourier transform of the impulse train, and we have the Fourier transform of each individual period is continuous spectrum P of f. And now we go in and get the Fourier transform of the impulse train. It's Fs times, the sum of the impulses. Put it all together. This guy doesn't get used directly. It gets used in a sampled form. So we're just going to sample it at multiples or harmonics of Fs. So that becomes what's in the blue box at the bottom. That becomes a Fourier transform pair for periodic signals, which in reality is telling us, and we'll see this after the break, that the Fourier coefficient is actually sitting right in here. That's the Fourier coefficient right there, x of n. And we did not have to do the Fourier integral of one period. We instead just considered it to be, the single pulse. The P of t becomes P of f, and you Fourier transform it. To me, it's very vitally important. To you, it's going to have to grow on you. So I'm going to let you go take a break right now, and it'll start maybe percolating through your brain, and your big wow moment won't hit you for a while yet, or maybe never will. I mean, I was always taught myself that don't expect all the students to come to the same realizations at the same time. I mean, I think a lot of things in engineering don't hit you until you're working somewhere and it's like, hey, I remember something like this, and all of a sudden you have this moment where all of a sudden all these things coalesce in your brain, and it's like, wow, I really get this now. But why did it take so long? I can't give you the answer to that, but so it's about 9:25. We'll come back at 9:40. It's good by me. So I'm going to pause the recording. Okay, coming back to the second half. We just had a crash, but I think the video for the first half is safe, and I will have a new video to merge with this one. So we were just talking about this theorem, and we'll look at an example of using it right down here. This is a pretty simple example, but it just says, suppose you have two pulses. This is not a waveform that I really know what to do with. It looks like building a house. It looks like putting a foundation rectangle and then a narrow one on the top. But to show you how you'd get the Fourier coefficients for that and get the Fourier series, you just write out what is the Fourier transform. You know it's two sinc functions. Then you replace f by n times fs, because that's what is going on in here. That is because of the sampling action of the delta function. It only sifts out P of f at n times fs, so you make that substitution, and then you roll down into here, and you've got the spectrum of the waveform, and you can conclude actually that those are your Fourier coefficients, but you can generate a line spectra. The line spectra plotting routines that are in the notebook still work. There's one for doing them in DBM that's in Lab 2, so there's a variation of the line spectra plotting that you use in Lab 2, and that allows you to then theoretically get line spectra to compare with the measured line spectra. And hopefully everybody in the lab brings a thumb drive every day so that you can just get the CSV file, because the idea is to overlap. And things like this happen in industry too. You're doing simulation modeling. I worked on a transmitter for the Blue Moon project, and we had to have a filter that met the NTIA spectral emissions requirement. So further down the line, when the development of the transmitter got going, they put a spectrum analyzer on there, got me the capture from the spectrum analyzer in the lab, and then I merged that with my theoretical expectation and then overlaid them, and then showed that at a meeting one day and said, we're doing good. We had different options on the filter, and we made some comparisons, and being able to overlay in one tool is contemporary. The old-fashioned thing would be to have a picture and then look at two pictures side by side, and that's too crude by today's standards. Hopefully all of you agree that if you can get the two data files together, then you feel much more comfortable about matching things up. So there is another identity, the Poisson sum formula, which is just briefly talked about in here, but the bottom line is this, and that's, I'm not going to take the time to go through the theorem, but it confirms to us when we have the Poisson sum formula that indeed x of n is fs times p of f with f replaced by nfs. So that seals the deal on, this as being x of n. Okay, now we're going to move into a very powerful and necessary topic, and most students don't appreciate this right away, and I'm going to try to impress this upon you. Those of you in the lab have been doing it all along. You've been working with the power spectral density because that is what the spectrum analyzer in the lab shows you. You haven't been working with the Fourier transform of the time domain signal. You've been working with the true power spectral density. The spectrum analyzer estimates it with analog processing or digital processing. The PSD function, which I've showed you in some examples in the Jupyter notebook, it's also doing a digital, DSP-based version, but it's the power spectral density. It is not simply the Fourier transform. So how do we get that relationship established? So we start with energy signals. And an energy signal, we know that g of f, we talked about this last time, is just the magnitude squared of the Fourier transform of an energy signal. And that was, I'll just dial back to it for a second since we had this just last week. Energy spectral density falls out very naturally for an energy signal as just being magnitude squared of x of f. You do a units calculation on it, and assuming a 1 ohm system, it will work out to be units of joules per hertz. If it's a 50 ohm system, you just have to divide by 50 rather than 1. But it works out for an energy signal. But that's just a single isolated pulse in most instances. So we want to have it for a power signal, which is generally periodic or a random signal, something that goes on for a long time. So we'll drop down here, get back into this idea. So we start at we go at it by saying we have the energy spectral density. If we integrate over the entire frequency axis, we get the energy of the signal in joules. So for power signals, we want to define a similar function. We're going to use the term S, tradition, S, power spectral density, something that we can integrate and get the power in the signal. Maybe this goes back to power system somewhere or another too, I don't know, because we are getting power. But we're talking about not a 60 hertz type waveform. We're talking about, communications waveforms, and that's where the power spectral density applies. So we have some function, S of f. What is it? Well, it's going to be related to the time average of a power signal, x of t, but we're not really saying what that is. It's just sort of a surmising because it's consistent with the energy signal. We also see that because it involves a magnitude squared buried inside of it, it's going to be real and even if it's a real signal underneath, and most importantly, it's non-negative. This is something that when I teach random signals in COM2 or in another class, I always talk about power spectral density as being non-negative. And the quirkish thing about this, and maybe this is connected to power systems too, if a signal is coming out of a generator, it's always going to be a non-negative power. What would happen if you could produce a signal that had negative power? It would be like it could suck energy out of something, right? It's just kind of, it's a bizarre concept, but we always think of a signal as being real complex, positive and negative valued, but a power spectrum is always non-negative, which means if it's coming at us down a transmission line, getting delivered to a load, it's going to contain a certain amount of power in watts. And if x of t is periodic, then S of f is going to consist of harmonics and impulses at harmonic locations. So as an example, if we take a cosine and look at its power spectral density, bear in mind, this is just an intuitive thing right now. Intuitively, it should place a it should have two spectral blobs, one at f naught and one at minus f naught. For the case of the cosine, they're going to be delta functions, so it's very precisely pinpointed at minus f naught and plus f naught. And because it's a real signal, the power is going to be distributed between the positive and negative frequencies equally. So the total power should be a squared over 2. That's our RMS idea from way back in circuits. Amplitude squared over 2 watts. So in the case of the power spectral density having positive and negative frequencies, it's going to be a squared over 4 at each of the two different frequency sites, the two blobs. So how are we going to get there? And this, I think the reason why we're having to skirt around so much is because if we were to start with a random process background, which would build upon probability, random variables, and so on, then we could get at it more directly. But we're trying to skirt around it to avoid having to dump in more stuff, random processes. So we go at it through the autocorrelation function. And the autocorrelation function ends up being a very valuable quantity unto itself. So we look at the nature of what is the autocorrelation function going to be? And what does it even mean to talk about an autocorrelation? Well, correlation from random variables, two random variables are correlated if they are statistically coupled to each other. Now, some of you haven't had probability in random variables yet. Some of you are taking it now, but everybody's at least taking it or has had it, right? So correlation in the probability sense means that two random quantities are related, right? Because they're correlated with each other. And we use this in our way of thinking. Statistical people say things. I guess psychologists and sociologists talk about correlation probably a lot too. It shows up all over the place, the notion of correlation, but we're in a mathematical sense here. So a waveform is correlated. If I can take the waveform, and this is going to be it going down the time axis, my thumb up in the air is like a marker, and I take the same waveform and just slide it past it and integrate it as I'm sliding it. When they're perfectly aligned, I get a strong correlation. When they when they're out of alignment, then the correlation dissipates because of the fact that they're not aligned with each other. And that's exactly what we get for this phi of tau function. If we go into the energy spectral density idea and break it down into the product of x times x conjugate of f, and then use convolution in the frequency domain because we're doing multiplication. In the time domain, we get a convolution. Actually, we're doing convolution in the time domain. So what happens, though, is we have a conjugate on one, and we don't have a conjugate on the other. And for a real signal, the conjugate means that the signal is flipped. So if we have a conjugate in the frequency domain, it means x of t is actually x of minus t. So we're actually convolving x with x of minus t. But what the result of that is, when we make the substitution in the convolution integral, we see that the convolution integral becomes a correlation integral. And this is the idea that I was talking about with my two hands, and the two waveforms of my hands are identical, I guess, except mirrored, lining up with each other. So we have x of t times x of t plus tau, and that is a correlation integral as opposed to a convolution. So what's the difference between the two? And you were taught this convolution says you take one waveform and then you flip the other waveform and slide it past, right? So now we're talking about correlating a waveform with itself. That's what auto means. Auto means self-correlation. And we're going to slide it past without flipping it. And that's why the extra minus sign is in there to represent it as a convolution. But when you take it into account inside the integral and you do the variable change, it becomes the correlation. So this is the correlation idea. Try my pencil and see if it works at all today. Does that make sense? You can do it with a sequence and DSP. Other things in correlation from prob and stats are more of a notion. You know, one thing's correlated with another because of something. You know, I'm only thinking somebody will say genetics, there's a correlation, right? Why do your children look like the husband and the wife? There's some correlation in there because of the genes and everything, but we're not in that domain. We're just in math. Math is more concrete in my estimation. So we're going to correlate a signal with itself. And we observe that out of this notion then that we can take the Fourier transform of the autocorrelation function for energy signals, and we get the energy spectral density. So the ACF, as it's denoted here, is a measure of the similarity of a signal at time t to the same signal at time t plus tau. And for the energy spectral density case, we kind of have this pictorial view. We can go directly from x of f to get magnitude squared of x of f and call that the energy spectral density. But now we can also take an indirect path. We can first take x of t, do the correlation integral, get autocorrelation, and then Fourier transform that to get the energy spectral density. Which would you rather do? The top one, probably, right? Because it just seems like I'll get there faster, no intermediate step. But for the power spectral density, we can't do that. So that's why we're leading up to it kind of carefully. So take the time average of a signal times the signal shifted. This will be the correlation integral, but it's going to be for a power signal. So we have to have this limit out here. covering the entire time axis, and this will give us the autocorrelation function. So this is the autocorrelation function for a power signal, and it involves a special case if it's periodic, which is most of the time for a deterministic signal, but for a random signal, it won't necessarily be like this, but similar ideas though. We can work with one period if it's a periodic signal, and then this is not so daunting. We just have to take one period, correlate it against a period, and then we can look at how it changes with tau. We can also observe that if the offset here, tau, is 0, this just becomes the total power. So that is going to tell us then that the integral of the power spectral density will be the autocorrelation function evaluated at 0. So now a little bit more hand waving here. If the Fourier transform of an autocorrelation function and an energy spectrum are a Fourier transform pair, it's a reasonable assumption that for a power signal, the autocorrelation function and the power spectral density are also a Fourier transform pair. In chapter 7 of the book, this gets described as the Wiener-Khinchin theorem, which those names sound German, don't they, if you know last names? My heritage is German and Norwegian, so we have that. It was developed a long time ago, though, by these two guys. So we have this established that if we can get the autocorrelation function, we can Fourier transform and get the power spectral density. So for power signals, we're stuck with the fact that in order to get the power spectral density, except under certain special cases, we have to first get the autocorrelation function, and then we can go on to get the power spectral density. So there will be some homework problems on doing this, but there are some things that allow us to get there faster. And one of them is for things that we have a Fourier series representation, and we can get that traditionally, or with the theorem we looked at before the break, we can get the Fourier coefficients, and we can get the power spectral density from that approach. I'm pretty sure I talk about that approach in the lab. So those of you taking the lab number 2 is pretty math dense, but it does involve a lot of power spectral density type analysis. So autocorrelation, that function at time 0 is greater than or equal to the autocorrelation at any other time lag. Intuitively, that makes sense, because if two signals are perfectly aligned, they're going to get the most correlation at that value. Then if you lag them off, the autocorrelation is going to decay. So it's going to be less than the value at 0. But if it's periodic, then we also know this will be true. It will come back and peak a second time, third time, fourth time, fifth time, because the period will shift between, or the period will be constant, but if you shift a whole period, it will be back at its peak again. The autocorrelation function is non-negative. That's number 5. Then properties 2 and 3 are thrown in there. Property 3 is kind of hard to get a handle on because we don't really have any power signals that aren't periodic except for random signals, and we can do that in the computer, but I'm not teaching you random process theory. I'm just mentioning here, though, frequently used with random signals, and we will be using those in simulations, but I'm not going to, like I said, teach you the theory. It's in the book. It's in the notes for the 5630 class. Our main focus here is autocorrelation, assuming both signals are deterministic function. And these things are pretty important for this class. Certainly right now in Chapter 2, but then they will carry on later to get the power spectrum. So let's just take a really simple case for a sinusoid. How hard can that be? Because we already guessed this a while ago, and it is exactly what we would expect it to be, a squared over 4, and that idea superposition holds so that it holds there as well. But at any rate, we can go in and just take this idea and do this correlation integral. Notice the t plus tau and the t integrating over one period. And now we get into using some trig identities. We're going to have cosine times cosine. So we're going to get a cosine of the difference and a cosine of the sum. And what happens when you integrate a cosine over a period or multiple periods? What do you always get? 0, right? You never forget that. It saves your life most of the time, right? In this class in particular, you can just say, this guy right here is going to go to 0. So this just comes on down, and it says, oh, this is interesting. The autocorrelation function is exactly the same as the function, time domain function, except the theta is gone. So there's no theta in here. And I do make an observation of that over here, and that is that the autocorrelation is, the term I use is blind to time offsets. It doesn't know about time offsets. The autocorrelation function is the same whether I operate on the signal shifted or unshifted. Okay, so this is pretty natural. Some additional properties. These are things that I maybe don't want to dwell on too much. This is kind of like for the square, or for the Fourier series, we had some properties. These are some similar types of properties. If we take and add a constant to a waveform, the autocorrelation function comes on through of the waveform, but there may also be a constant added at the end, or related to a squared, and then this, what is this guy right here? The average value, so that's the DC value, right? It's not cooperating with me. This shows up in the lab, because you'll be dealing with this and to answer some questions in the lab. And then the second one is the time shift property, saying it's blind to that. Interesting property to take things up one notch would be to take and sum two sinusoids together. And this shows up in the lab as well. And this shows up in a homework problem I was looking at. So I'm debating, should I make you do this in a homework problem? If two sinusoids, x1 and x2, are added together, as long as their frequencies are not the same, what's going to happen is when we take this product, quantity x1 of t plus x2 of t times the quantity x1 of t plus tau, x2 of t plus tau, what's the fundamental thing that's going to happen that's kind of a pain to deal with? We know we're going to have the first term times itself, the second term times itself, but then we're going to get what? What do we call this in math? When we're multiplying polynomials together, we get cross terms, right? Cross terms can be kind of a pain in the butt. Agreed or not agreed? It's like I got to remember that, and hopefully it's 0. Right? That's what you're going for. You're hoping it's going to be 0. In this case, it will be 0. So here we get 1 times the other for x1 and x2, and then we get a cross term in this orientation and a cross term in this orientation. They're not necessarily the same, but in this case, as long as f1 does not equal f2, what's going to happen is we're going to be integrating something like this from the trig identities again, and we're going to always average out to 0. So we're saved. What happens if they were of the same frequency? Suppose one was a cosine, the other was a sine. Then what would you have to do? This goes back to 2610, I think. The phasor addition formula, remember that? Does anybody remember that from 2610? That was like one of the first theorems that I remember in that book that you first learned about. If they're the same frequency, how do you add them together? You have to add them vectorially, right? You can write a cosine as a sine, and then once you do that, now you've got an amplitude and a phase on one term and an amplitude and a phase on the other, and then you can bring them together through that identity, which was back in 2610. Maybe I need to have a cheat sheet up for that or something. But if I give you a homework problem on that, you will have to recall something like that. In this case, though, we're assuming they're not equal, and so the average will be 0, and it's just going to be, the autocorrelation will be the sum of the autocorrelations, and the power spectral densities will be the superposition of the autocorrelation of the power spectrums of the two sinusoids. Very nice. Next type of waveform that comes along is a PN sequence, a pseudo-noise sequence. These are used a lot in testing digital communication systems. I'm using them in currently what I was working on coding yesterday in Python. It's just part of what I need to do for the system I'm working on. Remember I told you I'm working on a project called LunaNet, and I'm working on something called AFS, which is going to be a GPS system that will be around the moon, that will provide geolocation on the moon and have satellites that can perform similar to the way our Earth GPS system works. So PN sequences are the basis of our GPS systems, no matter where they exist. So the fundamental type of PN code or pseudo-noise code is a maximal length code, and maximal length codes can be created with a shift register feedback arrangement like this, where you have some XORing of taps in this shift register of D flip-flops formed with D flip-flops, and then you end up creating a pattern. In this case, this is a 3-stage in the maximal length sequence, and this is definitely a factor in the lab, those of you in lab 2. It's always going to be the number of registers, 2 to the 3, in this case, -1 or 7. So the pattern repeats every 7 bits. So in the case of the 3-stage generator, or PN3 as it would be called, there's 3 1s, 2 0s, a 1, and a 0. That makes what? How many different bits so far? 7, right? 3, 4, 5, 6, 7, and then it starts over again. Make sense? Testing that, stuff that I do or have done over the years, it's generally much larger PN codes than this, but a short length PN code ended up being very nice when I was working at the previous company, Taarca, Augustus Aerospace. I was working in the FPGA design, and I was working with an FPGA designer who liked hex displays of everything, because that was the way Vivado, the FPGA tool, liked to do things. And we ended up doing a short-length PN code so we could identify that we were getting what we were expecting to get, just because it made a difference in what we were doing there. And then we changed it to a higher length code, longer length code. So PN sequences have a number of properties, and how do you go from the PN sequence to the autocorrelation function? You actually have to go through and develop that, and that's a very long, tedious process. So in this class, I'm not saying you have to do that. We just know that this is what the autocorrelation function of a PN sequence looks like. It will look like a periodic sequence of triangles, and it will have a bias on it, assuming that the logic levels are 0 and A, which is what this picture over here was showing you. Well, no, excuse me, plus and minus A. So we're assuming it's plus and minus A. If you need to do a different logic level swing, like 0 to A or something like that, you have to go up and kind of make your way through this discussion in here, extend or utilize this very first property in here, and you can do that. That's part of Lab 2 for those of you in the lab. I haven't decided what I'm going to give the whole class in the PN code discussion, but at any rate, this is what it looks like for the logic swings of plus and minus A. And then we can use our theorem that we just came through, and we can get the Fourier transform of this periodic triangle with a DC offset using this theorem right here. And there's some ideas on how you might take into account Fourier transforming this. But one way of looking at this is to take the DC bias off of this, and then it's triangle sitting at 0, and then add the bias in later and just carry that on through. After all, what is a bias going to do on here? Let's just think about that for a second. It's 7 bits in the pattern, or in general, it's always an odd number, so there's going to be one more 0 than there is 1 of 1. So that alters the DC bias, so that's going to add a DC component to the spectra. Does that make sense? We'll end up with a DC spectral line in the case of a PN code always. In Python, I have the M sequence and then PNGen functions in the SIGSYS module. And these are kind of old. I didn't update this. I think I have more generator links in the library right now that are available. I just put the code in here. I didn't take it out, but you can see what it looks like. So we could go on and plot the spectra, and I think I actually do that down here in the Jupyter Notebook. I have the exact spectrum in here, calculated directly from the map that we just were looking at. And then I use the line spectra function to take the Fourier coefficients, and we already know how to get these Fourier coefficients because we were talking about that earlier from one period of the autocorrelation function. And then once you have that, then you can get the line spectra. So this is the exact line spectra. It does have a DC component. If you don't have a plus and minus A, you'll get a much stronger component at DC than what this shows, and that's what I think you see in the lab, if I'm thinking. But you actually don't see the DC value, so never mind, you don't see it on the lab equipment. Here's what we get for a PN code, though, that switches between 0 and 1. It will have that high value just because of the fact there's a different DC bias on the logic waveform. So this is an approximation, though, using this function, which you're getting exposed to I guess I didn't use that one in here. I used FS coefficient. I'm thinking of what you do in the homework problem. I was looking to see what did I do in this with the homework problem. I don't have that in there. So, or did I skip over something that I had in here that I never showed? I was trying to think, where did I use FT approx? I think I used that in here somewhere. Does anybody have any questions on that function? Because you've been using it in the homework, 2 people have turned it in, a 3rd person showed me their work. That's a function, though, that you get to use. The function I'm talking about, I'm just going to, since this is cleaner to look at, I'm going to go look at this guy. I'm supposed to fix something in here. I didn't fix this after I messed it up, so. Oh. Something got replaced in there. Watch out for things like this. I don't know what I did to make that happen, but it happened. See, VS Code is very quick about letting you know as soon as you type in a letter, it's telling you all the function names in the module SIGSYS that FS, and I was talking about FS approximation. So, and if you hover over it, it will give you all the help that's into the file itself too and how to use it. So I think I've given you good information on this in the hints for the problem, for the homework. So I think, unless somebody has a question, I'm pausing because we're getting close to the end of the period and the homework is due. So is everybody okay with using this? It works very well, and actually it relies on another function that you learned about probably in terms of MATLAB, but it's here as well in Python. So we'll go into the signal module, which is part of SciPy, and there's a function in here called freq_z, which MATLAB has, but freq_z allows you to take a discrete time signal and get its Fourier transform of a sequence. So that and the FT approximation are really one and the same. If you were to look at how I created it, I'm just taking the discrete time Fourier transform of a sequence and modeling it as if it were continuous time using a finite number of samples at some spacing, which sets the sampling rate and that relationship. I'm guessing you used freq_z in 3205. True, or don't you remember it? Did you like the function? It's to me, it's the backbone of modeling and everything, and it turns out it's under the hood and right here in this class. So it's just sort of disguised a little bit, but not too much. And what's the nature of freq_z and what makes it work so well? The fast Fourier transform is under the hood of freq_z. So we've already talked about that in here. So that's one of the pillars of DSP, actually, is the fast Fourier transform. Okay, so another little development in here, though, that relates to the lab and can relate to homework problems is how do we go from what we did before break with periodic signals and getting their Fourier transform to now going with autocorrelation function, power spectral density for periodic signals, which means they have Fourier series. So we can take a step back and say, if we had a Fourier series representation, we could get its autocorrelation function. We should be able to get it by taking the time average of this double product, or this product of two series. And this is not something I want you to dive into and totally get a handle on, but you can take one series times another series with a conjugate, and we're going to get lots of terms. I mean, it's going to be a matrix full of terms, but the matrices have infinite dimensions, so it's kind of mind-boggling. But this is what it distills down to. You get cross terms, which go away, and then you get the terms that survive out of this, which track up and down with each other into a single sum. And then the net result of that is you get that the power spectral density, and this is a very powerful result, especially for those in the lab, is just going to be the magnitude squared of the Fourier coefficients, and the magnitude and the Fourier coefficients are just Fs times P of f evaluated at n times f naught. So it distills down to say that you can get the power spectral density kind of without having to get the autocorrelation function if you go take this passageway. And some of you have been working in the lab too quite a bit. Have you bumped into this? Is this familiar to you? Because I'm pretty sure I put it in there. I mean, let's face it, math gets messier the harder you push on something, and the harder you push on something means that you're looking for something to make life easier. If you're like most people. If you like the pleasure of having hard work to do all the time, go for it. But I like to figure out a way of getting around some of the hard work, and this is a very nice thing. So here I did a modeling. I showed you that already. Okay. I'm done with that for now. This is what we'll do next week, but I'm going to skip over a lot of this and probably not give many problems on this. But what I want to do now is talk a little bit more about autocorrelation function, because power spectral density, I think I've been through a bit already for those two types of waveforms, the sinusoids and the pulse train I didn't do, but I've shown you that in general it relates to the Fourier coefficients, which relates to one period, Fourier transform of one period. So I realize that hasn't fully assimilated in your brain, but just keep thinking about it. It's all related, and taking the Fourier transform of one period is very fundamental. I mean, what does it bring back to mind? It brings back to mind that we have, let's see, comes back to mind that we have theorems and we have transform pairs. You can base pretty much all your work out of this, and then think about using trig identities as needed to kind of bring things together as well. So now what I want to do is just talk about where autocorrelation itself, not the power spectral density, but where autocorrelation comes into play. So a project from Modern DSP that wasn't run this past year, but I have used before, talks about GPS, and I'm just going to give you an overview of where autocorrelation pops up in GPS. So this is, the original program was called Navstar, which stood for Navigation System Using Timing and Ranging. It's been around since 1973. I can relate to that, but you guys can't because you weren't born yet, I don't think. But it's all these satellites that are flying on medium Earth orbit, so they're constantly moving around with respect to a footprint over the Earth. So what are those satellites? What are we going to do with those satellites? We're going to try to find our location using ranging to satellites. So if you range to one satellite, you don't know exactly where you are on the Earth. If you range to two satellites, you have an ambiguity as well. But if you range to three satellites, you can get solutions. One solution is on the surface of the Earth, that's the third picture there, and the other one is inside the Earth. So you're going to be able to resolve that too, because you're not going to have an elevation that makes any sense. More satellites, the better though. But this was something that was thought about in the beginning. I'm just looking at pictures here. So we have a code that is like a PN code. It's called a gold code. And what goes on is the cross correlation between those signals are looked at. And that was in the notes. I just kind of skipped over that because I wanted to get into this. But a local code is available in your receiver or your cell phone, and then the satellite is broadcasting another code. And the codes are arranged according to the satellites, and the satellites are always referred to as space vehicles, so SV, SV1, SV5, whatever. If you ever work in this, you'll be familiar with that terminology. So we have a course acquisition code called the CA code, and that uses a gold code of 1023 bits, period. A gold code is actually a combination of two PN codes, and you can create a family then of approximately orthogonal codes. And why does orthogonal codes matter? Well, orthogonal codes matter, and it did in second generation cellular, which was code division multiple access. I'm going to guess most of you remember that. Remember generation 2, CDMA, Qualcomm, which is a very pervasive company. Snapdragon processors, they're into all kinds of things. They're a company that's very smart, and they founded the CDMA concept from military communications, decades before that. At any rate, they all use similar ideas. A family of codes are all the same period, but they're different enough that they don't have a strong autocorrelation when you do cross correlation. So you have an I and a J in this case, and they don't correlate that well. So each satellite can use a different code, and then at your receiver and your handset, you can start tracking the individual signals. And how do we track the signals? We use some phase lock loop type of mechanism, but it begins with this. The transmitter puts out a code, particular PN code or gold code for that space vehicle. The user has the catalog of of all the different gold codes in it, and it's going to do some correlating. It's going to have something called an almanac, so it knows based on time of day from past exposure and past searching from the data that comes down on the GPS satellites, what satellites are going to be overhead at this time of day. So it can narrow things down and get locked up faster. Has anybody ever experienced, I can't get a fix, my phone, well, good example is travel somewhere with a GPS device, and it might take longer to get your first position fixed because when you show up in a different part of the earth or something, haven't had your phone on, it doesn't have its almanac updated enough. Has anybody ever had that happen? It generally happens really fast, right? Because your phone is in your pocket and it's already connecting. But if it was kept in the blind in the dark, it would maybe take longer. But at any rate, it knows from a family of codes which ones are most likely going to be overhead. So it cross-correlates, and that cross-correlation is the same triangle shape that occurs in the case of GPS every 1023 chips. And then it can track on that and get a time delay called the pseudo-range, and from the pseudo-range measurements you can then triangulate and solve a system of equations and get your location on the surface of the Earth. And to a lesser degree, with the pseudo-range measurement, you can also get elevation, although it's generally not as accurate as the local X and Y coordinates. I actually have something that I created called GPS Helper with our lab instructor, and with this system we're using a Kalman filter to take the pseudo-ranges and actually get the location through a trajectory. And this was just a picture I created for the GitHub site. And that red dot on the Earth is Colorado Springs because the model I put together with satellites in motion was based on the two-line element sets for the satellites. So those tracks that you see of the 4 satellites overhead is over a rather short period of time because they're always moving. Does everybody understand that the GPS satellites are in motion, and some fall out of view and then another one hopefully comes into view? So ECEF is Earth-centric, Earth-fixed coordinate system. So we can be very selfish, Earth-centric, Earth-fixed. It's saying everything revolves around me, the Earth, that is. Does that sound good? I mean, that's another thing you can get involved with that is kind of amazing for electrical engineers. We get back into orbital mechanics, things you learned a little bit about in physics, and you can start spinning up on all that knowledge and building that into your understanding. So what else do I wanted to do? I talked about the GPS idea. So what you have to do with the GPS system is you have to be able to track it, and this is kind of what goes on in the system. I'm going to show you one block diagram. For a given channel, you have to come in and do a course code search over the CA code, course acquisition code. Then when you find it, you have different correlators that are running here, and these are in DSP, but you have what's called a prompt correlator and then an early and late correlator. And from the early and late, which is skewed by, say, half a chip period, and it's 1.023 megachips per second or bits per second, you can then form what's called a discriminator function, and it relates very much to what you would have learned in control systems. And some of you I know had that class last semester. What do you do with a feedback control system? You have some sort of an error function which can drive you to 0 with negative feedback. Some of you got exposed to that. Others of you will see that when we talk about phase-lock loops. So that keeps you tracking the code while it's in view, and then you can get the pseudo-range measurement. So this project dealt with all the algorithms under the hood and tracking the PN code. Another very interesting application, which I got involved with, is geolocation. of emitters and things, and this is something that's been going on. I'm not teaching as much theory right now because I just want to motivate you to say how correlation is so important unto itself, not just the power spectrum, but the cross-correlation between a signal and another signal. So this paper was put in front of me quite a few years ago, Algorithms for Ambiguity Function Processing. And what is an ambiguity function? So let's just kind of drill in on that. I realized this PDF came off of the IEEE Explorer, and it's from a fairly old paper, so it's not, it was scanned in. So DTO and DFO is talked about in this paper, and it says differential time offset and differential frequency offset. And the ambiguity function is this equation 1, which takes a signal 1 and correlates it. And why can I immediately call it correlation, do you think, from what I've already talked about today? Remember, convolution, you have x of t times y of t minus tau, right? And that means one is flipped over as they're going past each other. If we're doing correlation, the waveform, and the same waveform for auto or for cross-correlation, they're both going in the same direction, so you're just skewing them one to the other. So this tau here is a correlation. So this integral is an autocorrelation, or is a cross-correlation, and then the e to the minus j2 pi ft is going to act as a frequency translation inside that integrand. And what it's going to do, it's going to say, we don't know a priori how S1 and S2 are related, but we do know is that one signal is not time aligned with the other, and one signal may have a Doppler on it. It may be shifted in frequency. So the idea is this ambiguity function comes out in two variables, tau and f, and it allows us to figure out how the two signals come into alignment. It'll give a peak on the time axis of when they're time aligned, and it will give a peak on the frequency axis when they're frequency aligned. So we can use that to do geolocation. And what is geolocation beyond what I was saying with GPS? It might be, we have some emitters sitting out there that, unbeknownst to them, we're able to intercept them, and we can then determine where they're located. Does that sound okay? I mean, it's been in movies for sure, right? People know where other people are because they don't turn off their transmitter. If you didn't have a radio on, you would keep yourself from being found. But if you do, then, and you're emitting something, somebody can lock onto it and do geolocation. So what this does is it lets you compute this function, this ambiguity function as it's known from radar theory. And it's sometimes called a complex ambiguity function calculator or cross correlation. Cross correlation is a better terminology because we're correlating two signals together. So I put together, this is the Marimo notebook, which is different from Jupyter. It's got some nice features, especially you can do GUI stuff. I've been working on some development for the first project right in here with digital modulation. These are all functions that are in our code package that I put together. This is gray encoding for quadrature amplitude modulation, of which BPSK is a subset of that, and then another function down below here that I'm just showing you how Marimo, there's the PSD we've used, but I've got gray decoding for quadrature amplitude modulation. So this is a simple digital comm link with analog information flowing over it. But to take another example, complex ambiguity function, I have a function inside of, so I got to get this to open up. The code gets hidden in here, so I have to open it. Okay, so I'm showing the code that goes beyond the picture. In this case, this notebook allows you to put the results above or below the code cell. So here I have it above the cell, which is the opposite of what Jupyter does. But here I have a function called streaming CAF. or streaming complex ambiguity function. So I'm producing a waveform that is just noise going through a filter, and I'm just using that to show how simple the cross ambiguity function can be for locating things. So the signal is just a noise signal going through a filter, so it gets a very specific squiggly shape to it because the filter is giving it a characteristic of whatever the filter's impulse response is. So then I take and produce that waveform, and then I produce a snippet down below here, which I say is going to be a reference waveform. So I create a reference from just 900 to 1200 samples. So I'm now going to put that reference waveform into my ambiguity function and use that as like a key to identify correlation with this unknown signal. So I purposefully maybe have put up a waveform that has this key on it, but now I want to use it to identify an unknown signal that I know also has used this key. How does that happen in practice? It might happen that you have patterns that are put on communications waveforms for synchronization. So they all do this. They just do it in order to function as you want them to function. You might do this on purpose. You might actually emit something and realize it's going to go up into the air and it's going to come up through another satellite and come back down again, and it's going to be embedded. So you can play a lot of interesting games, but at any rate here I'm just going to do the complex ambiguity function or cross ambiguity, and I've got zero frequency Doppler on there, but I do have some delay, and if I shift this, and this is just using some of the sliders, you can see there I've put 15 hertz of Doppler on, so now the peak has gone to a different frequency on my two-dimensional plot, or 3D plot actually. So we can find the location of that peak, and we can get its time offset, and we can also get its Doppler, and then we can use that for geolocation. All doing correlation processing again. Is it making your head spin a little bit? It's all very exciting stuff, and it's all stuff that's done all the time now. Maybe it makes you feel creepy, I don't know. But geolocating people in an office building, geolocating objects out in the world, you could be tracked inside a building now with algorithms that revolve around this. You can know if you're carrying a device, of course. You have to be emitting something. So we're pretty much out of time. This is the Marimo notebook, though, too, that I showed you. That's just a calculation that's done. It'll be part of a demo, but your first project, you'll be doing a lot of things, and you can do this in Jupyter, too, listening to things. Do something and then listen to something and understand what's going on. So amazing signal processing that you can carry out to do communications applications. So any questions on homework or where you're at? You're turning in problem 1, 3, and 5. 5 is playing with a smoothing filter called a square root raised cosine filter. It's used for digital communications. It was actually used right in here. I didn't make this bigger like I could have, but that SRC is the square root raised cosine pulse shape that you're playing with in problem 5. It's used in digital comm all the time, so I'm wanting to get you exposed to a pulse shape that is used, and it'll factor into this project because I'm dreaming away, which is my excuse for not having graded homework problems, because I'm trying to come up with a cool project that will let you play with some stuff that relates to, real things. So it's a trade-off, right? Don't grade papers, but I come up with a fun project. But I will make progress, and we'll also be announcing when we finish this chapter, which we're getting very close to, when the first exam will be. We'll be talking about that too. It'll probably show up in the homework, though, my projection of where I think it's going to land, and then we'll talk about it next week probably when we want to do it. It'll be in March. It's not going to be in February, but giving you the heads up. Okay, I'll see you up in lab, and I'm going to sign off.
I have a question about